got my very first false positive back. Speaking of false positives, your last project is next week. Don't let that slide away from you. Which is about false positives and false negatives. I got my first false positive from YouTube today. When I got up at 4 every morning and I checked the email and I got just to let you know, we pulled down one of your videos called the binomial distribution because it breaks this rule from YouTube. And what the hell? And I look at what the rule is and it says, no one shall upload a video that includes web crawlers, spiders, or other web viruses, basically. And I'm like, okay, I didn't do that. And it's interesting, they pulled it down. So if anybody was trying to watch the videos and they got to one that wasn't there, I'm working on fixing it and getting it back. I have to just send them a letter and tell them what's going on. But it was interesting, they identified one of my 750 videos that I've uploaded as containing a virus.
It's not your fault.
What's that?
YouTube's run by robots.
I know, and the robots are obviously wrong every once in a while.
Yeah.
Which is why I'm calling it a false positive. It was positively flagged as spam, if you will, but it wasn't. So I sent them a note and let them know. I don't know what triggered it, but let's use this data point as a teachable moment for your robot. Obviously, this is how spam filters work. So when you guys get spam filtered from your email, it actually learns as you allow things, as you don't delete things and don't junk them, it creates a database of phrases that come in. You know, and it says, if the word cigarette comes in and it's okay, I'm going to let words with cigarette come in. If the word pornography comes in and you let it come in, I'm going to let the word pornography not be filtered. That's how spam filters work. They work by learning, and they get refined over time. Same as YouTube's robots. Same exact thing. Very, very often, when I upload music, I have an issue with YouTube because they tell me I don't have the rights to songs I've written, and that's part of the problem with the robots is they don't know that I wrote the song. I have to teach them that. So I'm going to teach YouTube that. But my apology is if you tried to get that video last week and it's not there, it will be eventually. I just have to get it cleaned up with YouTube. I'm learning as I go. So Bayesian filtration is what it's called. Bayesian filtration. And that's what your last project is all about, believe it or not, is Bayesian inference. It's pretty rad, actually. False positives, false negatives, and how to block things automatically without having to sit there and actually read through them yourself. Anyway, any questions you guys have about what to do? There's not much left to be due, really. I mean, we got one last exam.
Do you know where that is off the top of your head?
It's on the schedule page. I don't. Either Tuesday or Thursday.
He's looking right now. So
yeah. He'll know. I'll have the out-of-class part uploaded by this weekend. I'm going to make it this weekend so you have at least a week and a half to work on it. Not that you'll need a week and a half, but just like I like to give you guys that much time to work on it. And the in-class part will be whatever that time is. It will not be a 2-hour block. It will not be a final exam. It'll be a third exam. So it'll pick up where the last one left off.
Oh, okay. So it's not familiar with it.
Oh, God, no. I mean, it's already cumulative by the fact that we keep talking about things like averages and graphs, but it's not, I'm not going to go back to the first 6 problem sets and do that to you. Oh, God.
They were the easy ones.
What's that?
They were the easy ones.
I don't think this is going to be, I don't think you're going to be appalled by this. I remember I keep the in-class ones very topical, and I let the out-of-class ones be more deep. For example, the binomial homework that you guys looked at, there was a salmonella problem, I believe, that I find exceptionally interesting because you can actually use it to test across entire, you know, to see how to save money by testing for certain diseases. I would never include that on an in-class exam because it's dumb. It takes too much time, but I love it on out-of-classes because it lets you look at how a business can save money if they have to detect disease or something using a test with a certain reliability. That's a great thing to study. I mean, for anybody that's keeping livestock or anything else for that matter. But I would never do it in class because it's too much of a time crunch. So don't fear not, my friend. Fear not. Plenty of time. Plenty of time. They're all squared away. So you got an out of class and in class. That's 2 weeks. One more project. Bayes. There's a quiz. There's a couple of quizzes you can turn in today if you want to about the binomial. That's optional, of course. I'll have one more quiz for next week, and I think that'll be it. Holy crap. We're getting there. So keep checking those progress reports. Make sure I have the same numbers you have. And if I don't, let me know and we'll fix them. Okay, doke?
And the out of class is still the same day as
Same as day as the in class. Yeah, that's the thing that sucks is I can't go find you like Christmas. But I can not bad. So I have to bring in that. That's why I want to get it up this weekend so you have the same like the time you would have normally. Cool? Fantastic. Fantastic. Let's recap from Thursday. Where we were talking about the beautiful what? Yes, beautiful bell curve. And I know you've talked about it a lot in other classes. Even just talking to Tony, as I was chit-chatting with him on the way over here, I realized that so many people, and I love the fact that I make you guys write in assessments, and he's teaching statistics and assessments. Almost like all the classes are getting a little bit of everything. in talking to him, I realized that this is a pretty conversational kind of thing. You draw a curve like this, and you draw a bell. But what I like to do, what we're doing right now, is we're getting a little more involved in that bell and making sure we understand what's going on with it. For example, what's that? Good. The z value right there is going to be 0. And what does that mean? 0 standard deviations from? The average, which means that guy right there is your average. I'm going to put over here on the side the standard normal curve. The standard normal curve is going to have 0 in the middle. That's the program I gave you. The program that you're running on your machines is the st-normal. That's why it's called st-normal. It assumes 0 is in the middle, and then we bump out 1, 2, 3 as far as you want to go, -1. And what are these measures right here? They're standard deviations. The further out you get, the more unusual. The further you get, the more unusual. Here's 1 standard deviation from average. Here's 2 standard deviations from average. Here's 3 standard deviations, and so forth and so on and so forth and so on and so forth and so on. Very nice. Very nice. So that's the big takeaway. And the way we do probabilities on this curve is we identify, there you go, we identify a vertical line which chops either 1 or 2 z-scores, and we shade between them. And that was we spent a great deal of time on Thursday talking about. That's how it correlates to the 2-column probability distributions for the discrete ones. We just can't do it for this because this data is generally what? Remember why we drew it graphically? What kind of data do we generally have down here? Continuous, and it's infinite. That's the problem. You can't count between 0 and 1 because there's infinitely many numbers between 0 and 1. I mean, how far is it between the ground and the top of my head in inches? Well, first of all, it's constantly changing, and secondly, there's infinitely many data points between my feet and my head, most of which are poorly dressed today. So that's why we have this as a 2-dimensional graph, and that's why I gave you the normal, because there's no way to do that without using calculus. The program does it for you, so you don't have to worry about it. Cool? Fantastic. Fantastic. But now, let's put some context to it. Let's put some context to it. I left you with a question on Thursday. You probably forgot it already. Maybe you don't. I don't know. But the question was this. What percent of adults are dull normal? And you might remember this, and it's okay if you don't. I'm going to change the ink in this thing. This means they have an IQ score that's between
80 and
90. Yes, ma'am, 80 and 90. I'm going to change the ink in this real quick. That's the question I left you with. How do we answer that? How do we answer that? And you could say you don't know, because we're a little bit underprepared for this question right now. Could we go to normal? Could we go to normal and enter 80 and 90 into it? Could we? Could we?
Sure.
Yes. Should we? So here's the problem. We can. We can, but we shouldn't. And here's why. If you go to normal, and you put 80 and 90, you do it as a forwards problem, which we learned about, forwards versus backwards. You do it as a forwards problem. And not only that, but what? If you put 80 and 90 into the normal, it's going to assume that the average IQ is 0 with a standard deviation of 1. The problem with that is, this curve is great, and we can always get back to this curve. But we're going to have to deal with what I like to call general normal distributions, which are what happens when mu is not 0 and or sigma is not 1. And that's the problem with IQ. Not the problem, that's the condition with IQ, is IQ has an average of 100. Did we explain why the average IQ was 100 last time? Yeah. We did. The ratio of chronological to mental age, or mental to chronological age. And it's got a defined standard deviation of 15. That's what we have to deal with. So essentially, we have to deal with this. We have to deal with, can we put 100 there instead of 0? And the answer is yes. We just can't do it with that program directly. We have to do a conversion. So if that's 100, what would this be right here? 15 more than 100, yes? We have to add 15 to the 100, so that'd be 115, right? What would this be?
130,
Good, and this would be?
145.
Good, and then we keep going. And then what would this be right here? Is your 85, 15 down, yes? And then this would be? Good, and this would be? And now you're starting to get into, this is when I asked you what moron, imbecile, idiot, that's where these live. And these used to, I looked it up on Wikipedia, this used to be called precocious. Precocious, genius was somewhere up here. I think precocious was actually above genius. The labels have changed over time, thank God. Moron? I mean, that's become part of the conversational language, no longer just a scientific term. You're still chuckling about it. I mean, that's right, because we're so used to calling people morons. So where the dull, normal folks live?
Halfway between -2, -1, and halfway between -1, 0.
Is it halfway?
Ish.
Good. We're gonna tighten down that ish a little bit, Kate. Hold that thought. Yes, well, if this is 85, it's obviously, it starts 5 points above that, yeah? 5 points above that. And if this is 70, it's going to be 10 points above that or 5 points below that. So it's going to be roughly in there. Now, it's not halfway. It's a third or 2/3 of the way up and down from that. But this is where it gets, this is why I try to hide formulas from you guys at all times. But here's a place where I don't think it's good to hide them. I don't think it's good. I think this is a useful formula to have. If I had to turn that 90 into a corresponding z-score up there, what would it be? I gotta go for -3/4. Why -3/4?
Because it's a third that way of -1.
So it's a third, okay, so this is -1. If we went a third this way, wouldn't that be -2/3?
Yeah.
Does that make sense?
No, yeah, you're right.
No, it doesn't make sense, or it does make sense.
I have no
Okay.
idea why I said 3/4.
No, it's okay. It doesn't matter. We're gonna fix this momentarily and make it a much. And then what would therefore this guy be right here? -1 1/3. Good. -1 1/3. Now I'm seeing a lot of looks that are like, I'm terrified at this moment because we're doing fractions. And it's scaring me a little bit. Not a problem. Not a problem. There is a conversion factor back and forth. This is where the world lives. But this is where we get the answers that we need as far as likelihoods and probabilities. So we need a go-between between any general normal curve and the corresponding standard normal curve. And that go-between is only the second formula for this class we'll play with, and it's called a z-score, which we mentioned. I mean, we talked about these being z-scores. There's a formula that does the conversions for us as well. So I'm going to show it to you over here. Go over here. And basically, it's what Kate just did in her head, but in formula form. No. It's what you did in your head, though. You said it's ish halfway, and you said, oh, it's a third of the way. What you were doing in your head was you were figuring out how far down it was, weighted with the standard deviation. So, for example, think about this. Kate looked at 90 and said 90 is 10 down from 100, so it's -10. But the whole distance of one standard deviation is 15, so she did -10/15 and got -2/3. 80 is 20 down from 100, which is -20, divided by the standard deviation of 15, which is negative, as Robert said, 1 1/3. That's a formula. You take whatever the raw data value you have is, subtract off the average of the distribution, and divide by the standard deviation, and that tells you how far down, or how far up, depending on which way you're doing it, how far down or up you end up being on the distribution. So here's how you convert between a general normal distribution. Yep. And the standard normal distribution. It's a beautifully simple formula. It's gorgeous. It's even more simple, I think, than the average formula because it doesn't involve any Greek letters, which is nice. Okay, so here we go. I'm going to write the variables down first, and then we'll go back and make sure you understand what each one is. Because the formula itself is pretty straightforward, but I want to make sure you understand what each of the pieces is. That way you buy into what it means. It looks like this. Those of you taking 244 next term, you're going to get really used to this. And over the next 3 days, I'm going to make you get really used to it as well. This is the magic conversion formula. JC, don't you worry, my friend. We're going to deal with this right now. Each piece. Because I know it looks a little terrifying. It has subtraction and division in it, which are two of the not so nice operations in mathematics because they're not commutative. Let's start with the easy pieces. Two of those pieces are pretty straightforward. Which two?
Average.
The average is going to be given to you. This is going to be a given average, given to you in the problem somehow. So I'll tell you, on average, IQs are 100. Boom. Paired with that, Natalie Carter, what else? I got to give you this too. That's the given standard deviation. I got to tell you that as well. I got to tell you how to stretch the curve. I can tell you the average tells you where the curve sits, left to right. The standard deviation tells you how tight or loose the curve is. More on that Tuesday of next week. We'll get back into that more on Tuesday of next week. I promise you there. Those will be given, and that's a piece of cake. Now, in every problem I give you for this, I will then give you one of these two numbers. And this is where you have to understand the difference in the two curves. This is the z-score from the standard normal distribution. So that's the location on the zero-centered bell curve. That's the location on the zero-centered bell curve. The reference, if you will. It's the reference on the normal, on the program you have in the TI. That's the reference value. It will be positive if it's above average, it'll be negative if it's below average, and it'll be 0 if it's at average. And mathematically, this formula explains to you why all those things are true. We'll come back to that. What do you think that is right there? What do you think that is?
Variable.
That's the variable from the general normal distribution that you're converting. This is the conversion factor. If I give you this, this would be, for example, the 80 or the 90. You can feed that into this, which then spits out the reference value on the standard normal curve. So this is the random variable that you're given in the problem. This is your general normal random variable. Yeah. That's why I like calling it X again, with your permission. I like to call it X again, because that's what we're used to calling it. Random variables are equal to X. Just got used to that labeling. So that gives you a back and forth. It's almost like converting Fahrenheit to Celsius or inches to centimeters or something like that. You have to take the value you have, feed it through some conversion, and out on the other end pops the value you need. So we always need to convert because we have to turn these numbers into locations on this curve. And it's going to change depending on the context. Today we're going to look at IQ. We're going to look at human pregnancy. We're going to look at both of those things today and figure out where things lie on this curve. They're all going to come back to this curve. Every single one of them is going to come back to this curve. But our job is we have to do a little bit of work in between to do the conversions back and forth. And that formula, you're going to see all throughout 244. It exists in every time we do any new test in 244, that guy comes out because we like coming back to this curve. This curve is very, very special. It's very, very useful to us. Fair-ish? Fair-ish. Any questions so far? I know it seems a bit lectury. I apologize for that. I apologize. It's a little bit too much like, here's some information. Let's let it wash over us. It makes more sense when we actually start applying it to like things like IQ and pregnancy. So, shall we? Want to answer the dull normal question? What percent of adults are dull normal? I think we got it now. I think we got it now. So here's where we want to be. And this area I just shaded right here, that the TI will do it for you. It will give you the area, but what do you have to know? What do you have to know in order to get the proper area? That's what it's going to give you that, Robert. Now, Robert, I'm going to put a pause on that for 5 minutes because sometimes you're going to want the probability you put into there and have it come back with the IQ score. We'll do one of those also. But right now, we have the IQ scores. I want to know what people have, what percentage of people have those IQ scores. But we got to take the IQ scores and convert them to what? Say that again, Heather, nice and loud. We have general normal. We got to convert them to standard normal. We've got to get onto this curve. So I got to know. Now I know you guys have already given me the answers: -2/3 and -4 4/3. I want to make sure everybody sees where those numbers came from via that formula. Yeah. So We know that we have to be between 80 and 90. That's the area we want, is the shaded region between 80 and 90. Our job is to figure out, okay, when Sean says an IQ of 90, how many standard deviations from average is that? That's the question. That's what a z-score is measuring. A z-score is measuring standard deviations. So when he tells me they got an IQ of 90, how many standard deviations down from normal is that? And it's 2/3 down. Now, if you're not doing that in your head, that's the beauty of the formula. The formula will convert it for us. So let's run the formula twice. Once for the 90, once for the 80, and you'll see where these guys' numbers came from. Okay? So we'll do 80 first since it's over here. How far down is 80 from average? Well, it's 20 points down. 80 minus 100. That's x minus mu. If you look at the formula, x minus mu, 80 minus 100. So it's 20 points down, but that's not 20 standard deviations. My God. That would mean the standard deviation was 1. The standard deviation is 15. So by dividing by 15, it tells you how many standard deviations down it is. So you got negative 20 over 15, which is negative 4/3. Or as Robert said, negative 1 1/3. So it's past 1 standard deviation down. Past 1 standard deviation down. So if you're thinking area right now, you're in between that region of 2/3 and 95%. You're in that kind of gray area between. That's not that bad. That's exactly right. That's not that bad. Exactly, Jenny. You're not getting past 2 yet. We'll come back to that. Promise, my friend. Promise. Fair enough so far? Decent? Good? Yes, maybe. How about 90? We'll use orange. And we know the answer, and this was the answer that Robert said, the negative 1 1/3. Now, Kate gave us negative 2/3 this one. Make sure you buy Y. 90 is the score you got, the raw score you got on your IQ, or this person's IQ. The average IQ is 100. That's 10 points down. But that doesn't tell us how unusual that is. 10 points is relative to how everybody else is doing. That's where the standard deviation ruler comes in. So it becomes negative 10/15, which is negative 2/3. And you might remember Kate saying that number before. It's 2/3 of the way down. So now we know our 2 z-scores. Those are the z-scores for the standard deviations that are going to go up onto this curve, and the TI is going to shade between them for us. And it's going to tell us this percentage of people should have that IQ. Fair? I intentionally didn't let the program do the conversion for you. Because I'm a bastard, partially. But because I want you to get comfortable with that conversion. That's 244 is based around that conversion. Honestly. How many of you guys take a 244 again? About half of you, right? Yeah, about half of you. Oh, more than half of you. Good, awesome, fantastic. That formula is all about 244, converting back and forth between a general situation of data and then a standard normal curve that we have to go from. Ask me questions right now before we go to technology. Technology takes care of the answer for us, but make sure we understand why we got to this point first. Please, go JC, thank you.
Are there always going to be 2?
No, very good question. We'll come back to that when we answer Robert's question as well. Because you're not always interested in between. Sometimes you're interested in above or below. And that would only be 1. And we'll come back to that. Promise, promise. Fair enough? Fair enough. Okay, good. Good, good, good. So, let's figure it out now. Let's get the answer. What percent of people have IQs between 80 and 90? Okay? So now, I'm going to go right over here, I think. Put it right in this spot. Make sure you can see that on the camera. Not bad. Oh, it's taking pictures right now. Clever. Okay. Let's fire it up. Programs to normal. Okay. Is it forwards or backwards?
Forward.
It is most definitely forward. How can you tell it's forward?
No idea. You picked it.
No idea, you just picked it. That's a good answer. That's a good answer.
I remember.
Because you know
Because you're given the z-score. Oh, that's how
You guys got it. That's okay. And this is fantastic. Skylar's going like this. You know the horizontal axis value. I'm asking you for the probability. What percent of adults? I'm asking you for a percentage. Robert's asking about a backwards problem where you put in the probabilities and generate disease. We'll come back to that. But I like doing the forwards ones a couple times first and then reverting to the backwards problems because I think it makes sense. I think it makes sense. All right, that's a weird screen. It's not going away, so let me... Done. All right, program. What's that?
How does that work for you?
How does that work? Because I grew up in the 80s. That's what you had to do. Okay, we're forwards, yes? Yes, it just is. Okay, forwards, it's a between. This goes to JC's question. They're not always between. This one happens to be. Okay, between. Left bound
-4/3.
is your -4/3. You can put it in as a fraction.
Oh,
Right bound is -2/3. Are you seeing why they're both negative mathematically? They're both below average, yes? And that's the beautiful part of that formula. It takes care of that for you. It actually deals with it. Here we go. It's going to shade it for us. Here she comes. And you end up with roughly 16%. So by definition, 16% of people should be dull normal. By definition of what an IQ test is, and by definition of the fact that they tell me it's bell-shaped, which I have no reason to doubt because I know nothing about them. And Engineer Whittle keeps telling me that this sounds about right. There you go. 16% are dull normal. How's that sound? There you go. Good. Now it's like, oh, I like that. Now some people are like, that seems like an awful lot of dull normal. That's 1 in 6 people. Yes?
yeah.
That's 1 in 6 people. But realize also that 1 in 6 people are also what?
Other side.
The other side symmetric.
I don't know what they're called.
I think they're called bright normal, actually. I believe it's what the latest bright normal. So bright normal would be what, 110 to 120, I believe?
Yeah.
10 and then 20 points up. Yeah, so 110 to 120 also contains 1/6 of people. Yes? Also contains 1/6 of people. They would be here. So here's 1/6 more people. And there's a humongous chunk that's in here, yeah? What percentage is in here? What percentage is in here? You might remember this from yesterday, but you might not either. It's a nice number. See if you remember this from yesterday. I'm going to run the program. I'm going to run another forwards problem that we did yesterday. Remember this from yesterday? Roughly half of them. We calculated this yesterday. The first and third quartiles were about 2/3, 0.67, I believe, exactly. But it's close to 50%. So you got half of the population between 90 and 110. Half the population. That's pretty close to average. So half are there. You got 16 down on the dull normal and 16% up on the bright normal. So that adds in, what, 32% more. So you got 82% are between dull and bright normal. You feel better about humanity?
Yeah.
Maybe. You shouldn't make any kind of discussion until you understand what IQ actually measures. I don't know what it actually measures. I just know that that's how you quantify it. I don't know what it actually tells us, except that dolphins are smarter than us.
Yeah.
But that's what IQ actually measures.
I don't think that tells us the dolphins.
Well, that's what I've heard. And all I know is all I'm doing is quantifying. That's all I'm doing. So I'd like to quantify some more if it's okay with you guys. And I like using this because these numbers actually come up in discussion. So there were a couple forwards problems. What percentage of IQs between 90 and 110? Between 80 and 90? JC, we're going to answer your question, Robert's, both at the same time now. That's okay. There's an organization called Mensa. Some of you may have heard of it, maybe. It's called the High IQ Society. The High IQ Society.
Can we form a low IQ society?
No, because none of you would qualify. High IQ Society. Jack's shaking his head.
Oh, one of my aunts gave me a Mensa puzzle book.
And you did great in it.
No.
You did not do great in it. I don't believe that.
Like the level 1 puzzles were okay, but anything like level 2 I could get 1 or 2 out.
I wonder. I've never seen a Mensa puzzle book. I've taken IQ tests ad
Probably
nauseum.
also like 4.
Say that again.
I said he was probably also like 4.
Oh, so years ago. I got you.
Oh, you're
Well,
right.
here's the deal. Mensa's called the High IQ Society. So here was a forwards problem up here. I'd like to create a backwards problem now for you. Mensa. And the reason I like calling them forwards and backwards is it's a beautiful way of discerning. You can tell by what you do what kind of problem it is. Mensa. To get into Mensa. You have to score in the top 2% of an IQ test. They only take people that score in the top 2% of IQ tests. Here's what I want to know. How high do you have to score minimally to get into Mensa? That's all you need to know right there. Now, let's take a pause for a moment. Make sure first you understand the question. I want to know, I want to get into Mensa. Actually, I don't care, but suppose you want to get into Mensa. Or you want to get into some other training academy for something else. And they say they only take the top 10%. I think nursing programs like this, I think, right? Top 5% or something like that of the TEAS exam. The damn TEAS exam, certain percentile, right? Exactly, it's the same thing. Right. Now, I don't know with the TEAS exam if they're bell-shaped or not. So I'm not going to use the TEAS exam on this one because without knowing the distribution being shaped like this, I can't accurately. But IQ, I know is this way because I've been told it is. Why is this a backwards problem, first of all?
We know the probability, but we don't know our X.
Does everybody follow that? This is backwards from a forwards problem, which is a dumb thing to say. But think about what you knew with the forwards problem. With the forwards problem, I gave you raw scores. We then, gesundheit, we converted the raw scores to these beautiful z-scores, and then we got the z-scores into technology and generated probabilities from them. I'm going to make a little laundry list of that over here, if that's okay with you guys. I think this might actually be helpful. So for a forwards problem, this is why I call them forwards and backwards. For a forwards problem, step one is identify the raw score or scores. Identify the raw score or scores. Start with that. Start with that. Good so far? Number two is convert them to z-scores. Convert the raw scores, which are x, to z-scores. And the handy-dandy formula we need is this bad boy right here, which I will happily put for you on the board next week, 2 weeks from now when you need it. Don't worry about memorizing this thing. You'll probably memorize it automatically because you'll be using it so much, but I'll put it on the board for you during your exam. Don't worry about memorizing it. Okay? Once you have that, step 3 is going to be run the z-score or scores through your TI to get the percentage that you're looking for, and you're done. Because that was the whole point. That was the whole point of getting the percentage. And the question will have something like, what percent? What's the probability? Things like that. Things like that. What's the percent? What's the probability? Things like that. Is that fair enough? Fair enough. Okay. This is a backwards problem. The beautiful part about it being a backwards problem is you just have to reverse all of this. All you got to do is do all of this backwards. I want to take this out real quick because we don't need that. So for a backwards problem, and then I sense we're starting to get tired, so we'll take 5 and we'll come back and actually do the problem. You start with a backwards problem with what you ended with a forwards problem, which is good. You have a percentage. You start with a percentage. Good. You start with a percentage. Step 1, percentage is given. The second to last thing we did was run the z-scores through the TI. So we're going to run the percentage through the TI to get a z-score. We're going to run the percentage I guess we'll call it step 2, I guess. Or scores. Although I promise you, I'll promise you it'll just be a z-score. I won't make you do backwards problems that are between, because they're way too tricky. And they're also pointless. There's no reason to do them. So you got your percentage is given to you. Then you're going to convert the z to an x, and that means you can actually answer the question, what test score do you have to get actually get into Mensa, or get into the nursing program, or get into some academy training program, whatever it ends up being. And then boom, convert your z's to an x. It's the same formula. It's exactly the same formula, but algebraically, I think it's nicer if you solve it for the other variable. Because here's the deal. When you're converting x to z, everything you plug in is on this side. So when you go blah, 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 it kicks out this. if you're solving for x, you're going to have the z here, and the mu here, and the sigma here, and then you're going to do all this goofy algebra to kind of solve for it. So I think we should do algebra one time and then use the result of that. Can we solve this for x? Yes. Multiply by sigma first, get z times sigma, and then add mu over. So here's the conversion. There's your average plus z times sigma. And the reason I love that formula is sometimes that z is negative, which means you'll drop below average. And that formula takes care of you at that rate. Yeah. And I'll have that one, of course, written on the board as well during your exams, because don't memorize that either. Jenny, go, please.
What is that last symbol?
Oh, it's a sigma, and I always draw it wrong.
I'm sorry, I'm just gonna.
There. A little bit better. That's a little exaggerated. Yeah. I tend to put an extra little elbow on my sigmas. It's almost there. It's gotten worse through the day, I guarantee. That's not that good over there either. Little sigma. Populate. Here's the thing. It's given to you. You're gonna know that you're gonna know this value and that value. You're gonna know one of these two, and you have to find the other one. That's what the whole point of the problems are. Good? I'm seeing way too many yawns. Take a walk. And then come back, please. Go take a walk, and then we'll figure out how to answer this question we've got to deal with.